This week's video is a couple of different things. So the initial video on here is a job I tended to recently where E.ON had turned up and fitted a smart meter, and unfortunately for the customer, not so smart. They had a serious gas escape on the property, and E.ON turned it off, rightfully so. So I was then called in, and subsequently the issue was across a couple of different aspects, as you'll see if you watch the video. The second part of this video, I keep getting asked for more tips and tricks and fault finding stuff. So I've put together a couple of different segments to do with air pressure testing stuff. With that in mind, you'll see a couple of different tricks that I use to diagnose if things are going right or going wrong on the air side. Crack on and hope you enjoy the video. All the best, guys, and maybe I'll see some of you at FEX this week if I can get there. Have a good one. We've been called here to this job. The installer of the gas meter has condemned it. There's a leak on the system. So a couple of things straight away. So when you turn up to one of these, you'll notice how well things have been done. So they've turned it off. I've just turned it back on. So this is an Anton sniffer. This is a sniffer device for tracing weeps. It's not 100%, but it's pretty much up there for me. So I'm going to show you what I do to start this process, because otherwise it can take ages. So all of the appliances are on, and the first thing I do is I check. So this bleeps and it goes crazy when it finds a leak. Now the leak on this more than allowed, so we have to trace it. So I have got a standard gauge, but this is what I do. So come to the first appliance. I've got the cooker taken out, and this is on. So first thing, so you can hear it goes crazy. Yeah, I'm going to blow the gas out, because any residual gas can cause you issues. We're looking for a gentle beep. Excuse me, I'm going to need breakfast. Okay, so pop this in here. This is the most used hob here, burner. So we got a tiny weep already on that. Okay. Turn the isolation off. Next thing I do, typically, is I look for the boiler. So in this case, whoops, need my keys. If I don't have my keys, I can't get back in. So I'm also mindful of the meter, because I'm on a meter here. So I've got 15 minutes. So I've got the keys. So in this particular house, the boiler is situated outside. So come to the boiler. This is what I do, okay? It's not best practice or whatever. Find your way through all of the goodies, find the boiler. So on said boiler, I know that the system's still leaking now, so what I will do is I'll come under here. Now I know categorically that these in the past have leaked. Nothing. Just check the traces of the bits that I can see, go straight down the back, in amongst all the rubbish, nothing. Okay, so it's a bit windy now, so sometimes, bear in mind the gas is on. Check here, nothing. Check along the pipework, nothing. Okay, still nothing. Go around the back, nothing. Yeah, underside of the pipework, I can see some scaling and dirt there. Let's go to work. We're on the money. That's your break. That wasn't difficult, was it? And that's how I do find a tracer leak. Anton little sniffer works a treat. Yeah, now if it were somewhere else, we'd be in a lot of trouble. But in this particular case, it's not. So this is what I use. So we'll have to repair that, take all of this rubbish out. What a lovely day, eh? Look at that. This cupboard, I can't even get through the door. and I'm not big. Not in that way. Okay, so what I do is simply, we're going to chop this out. Okay, that's the first chop. I'm going to reroute this gas pipe across the front. Pipe slice this out. Okay, let's have a look. So there you go. That's where the leak was. Yeah. Straight through it. Right, so this is how far we've got. So I've put in a new piece of pipe. I've brought it across the front. I've sprayed it all with water because it's a little bit too close for comfort for me. For plastics, there's insulation down there, so I sprayed it with water. Hopefully that'll stop it from catching fire and stuff. So we'll just solder this up and then that should be us. We can check it. So it's Halloween and somebody left sweets out. Anyway, redone the pipework in front. He used that, and so turn this on and we'll give it a quick test. So I've reused this section here, this section, and just put on an elbow there and an elbow there. So well, that looks alright. I'm going to give you a little walk around my little experiment here. A 5-burner gas hob, and I'm doing some tests. Clearly, it's got thermocouples, electronic spark ignition. I'll just walk you through it. So 5 gas valves here. Yeah, each one of these has a runoff to each one of these. This one, the main burner here with a large wok type thing, has two jets here and a secondary one up there. And then these last two, small and medium. Okay, so you've got the ignition electrode here. This is just a stabilising bar. Here's what I've done. So if we turn this over, underneath here, this is your normal entry point into the gas hob. So what I've done is I've put an entry point in, capped off this side here, and we've got a test nipple here. And what we're going to do, so I'm testing this for leaks. So maybe you wanted to try and repair one of these, which is what I've done in this case. We had an issue on this valve situation here. Anyway, the point is, I'm going to show you how I deduce this issue. So this goes onto the test nipple, and we're using a very short hose on these silicone hoses. We're going to test the pipework that goes in here through this pipework that comes across here, goes all the way through and has a stop there. So in theory, somebody could have punctured it, or it could have degraded or whatever. Each one of these has an O-ring in it where it clamps to this bar. So you've got a bar going across here, a hole in each one, O-ring, and you've got what they call captive security bolts. So these bolts have a pin in the front, and the reason that they have a pin in the front is so that you can't get them mixed up with the ordinary screws, because if you were to loosen off one of these, guess what? You'd create a loose fitting onto there, which then would mean that it would spill gas. You take a gauge, standard gauge, put a silicone tube on it, nice short silicone tube, take a syringe, pop the syringe in, draw up the water till you get the desired amount of pressure. Pull the syringe back and twist it. As you twist it, it seems to settle the syringe. Now it's holding. So this is a 60 mil. So I've got over 30 millibar. Put this on here. You know where I'm going with this already, don't you? And release. What will happen is it drops down. We've got here 16 millibar, say. Yeah, 16 millibar. So we do a 2-minute drop test on that, see what it comes up with. I've done this several times on this, and there is no drop on the 16 millibar. Isolator back, turn the on, boiler back on, very low, so Probably needs a bit of a purge. Bingo. So we're back in business. I know I've got gas in the pipe, so just double check. Just in case any of you are thinking, oh, probably wasn't gas in it. So, and then I'll do my tightness tests. Yeah, happy with that. So let's go and do our tightness test, check everything's okay. Here's a selection of air pressure switches and switches of various types. Some I know about, some I don't. We've got a digital manometer here, and we've got an electronic multimeter here, and we've got a couple of different fans. So what I'm going to do is I'm going to show you a method to test some switches to see their functionality and a general overview. Switches in general, you've got two different types. So NC and NO, so normally closed and normally open. And what that means, circuitry that comes to these points will be in the closed position, so it'll be constantly closed, so it forms the loop all of the time when there's no pressure or no activity on this. So the second type is normally open, which is typically the most commonest. Most of these are normally open. So the idea there is that do not form continuity, so it'll have an open circuit. So I'll leave that there, and then you've got two different pressures often coming into these. Now this one's only got one, but the majority have two. One is called a P1 and one is called a P2. So one is positive pressure and one is negative. So if you will, one is pressure and one is suction. So the idea again is that on here they'll be labelled. So this one here is P2 and this one here is P1. And clearly the P1 is the positive pressure and P2 is the suction. This one here only has one. Let's get cracking. I have a syringe, T-piece, various silicon tubes. One is positive pressure for P1 and one is negative pressure, suction, for the P2. And this is set resistance continuity through. So initially I'm going to show you how I test these. It's to show you two different things. It's to show you that what you think is correct and what is actually the facts of what's happening. Put a syringe on one end of here, the other end onto one of these switches. So some of these are measured in pascals, some are measured in millibar. Pascals, if I'm right, was 0.01 of a millibar. Let's test the first one. So these two switches are exactly the same. First thing we do is we work out whether or not this is normally open or normally closed. You can do that by checking two of the pins. First of all, check there. Yeah, nothing, nothing, nothing. You can deduce from this that this is a normally open switch, unless of course it's completely faulty. Next test we do, these are 1 and 3. I'm going to swap them over. Turn the Anton on, draw some suction. If we zero that, draw some suction. Right, did you hear the click? Now, ordinarily, a lot of you guys I know test this by suction, boom. You hear the click, oh, it works. 0.72 millibar, so not even 1 millibar, and it's clicked. Now, I'm going to draw some more on this and you'll see. It's quite a bit more suction. Now, all of a sudden, we've got continuity. So at about 1 millibar, this goes clothesline. Still hasn't clicked off, so if I go down a bit more, there you go. So there's a massive disparity there, the click to when it actually goes clothesline. You can deduce that at about 1 millibar, this switch here goes clothesline. We'll just write on here 1 millibar. So exactly the same switch, 60 pascals. Put that there and do exactly the same test. Okay, 0 pretty much. Now we'll draw some suction, half a millibar, 0.6. So we're up to, now do you notice I'm drawing suction and it keeps going down to 0. What do you think? 0.64, then it goes down to 0. 0.47 goes down to 0. But let's draw it up. Click. It's clicked and then gone out. Clicked, gone out. But that's a faulty switch. However, watch this. If I draw fast, got 28 millibar and still got no continuity going through there. Just to double check. This one here, faulty switch, like that one. Come on to these two. These two are in millibar. It says the maximum pressure, 6 millibar. It's normally open. One on the top. So this is normally open, yeah? Because there's no buzzing sound on this. And on these they've got a positive and a negative. One says low, one says high. Some boilers work on positive pressure, like the profiles and things, and some work on a negative. Click. Now you've got 0.70 there, millibar. At 0.66, this will go closed circuit, yeah? Reduce, off you go. Let's try on the suction. Clicked. Draw it a tiny bit more. There you go, 0.66. At 0.66 of a millibar, thereabouts, this goes closed circuit. So that's well within 0.66. Okay. This one here, 3 terminals on here, same kind of thing. Choose the top one and the bottom one. Go with the low. Click. It's jumping around. This suction value here seems to be quite stable. It seems to click in, click out, click in. Just draw a little bit more. There's a click. Not dissimilar to this one. And this one here, 0.35. The maximum is 6 millibar. The other side, just in case anyone's curious. Now this is positive. There's a click. Stable. So that's those two tested. These have got adjustments in the centre, however you don't really want to adjust them unless you know what you're doing, and I'm not going to get into that in this video. Here's another pair. Turbo Max, things like that, an open circuit. Okay, so at about 1 millibar thereabouts, this goes closed circuit. So I'd be happy with that one. Let me take this one. 1.2, 1.3. Sorry, I forgot to say this one's 130. This one's 105 to 90. 1.5, almost. Got a click, nothing. So we've got a click. Stayed open. Now with that click, you would have thought that that would have gone. Draw a bit more. Draw a bit more. 1.4. It's still clicked at 1.5. Now all of a sudden at 1.5 it clicks in. Depending on the age of these, they'll either click straight in or they form resistance. Dirt, I guess, moisture. You could get temperamental issues with things like that. So that to me, I'll put a little X on it. Our last two. So first thing we do again, because it doesn't look like any of the others, there's 2 numbers on here and typically it's 1 and 3. There you go. So that shows me straight away that this is a closed switch, so it's normally closed. And then draw some suction. So we got the click, apply positive, there you go. So on the profile there's a positive and a negative, and depending on the two, it will produce in here an open line or a closed circuit. And the boiler will know that the air pressure switch and subsequently the fan is working. And now last but not least, I don't even know what this came off. 2 terminals, so we've got no pressure in here. Okay, so straight away we know that this is again closed. If I add some pressure, there you go. So you've got 11 millibars or thereabouts. Now the interesting one about this is this factor here. There's a screw on the front, so we had 3. So in theory somebody could have gone, hey, let's tighten that up. So it was 3 before. Now what? 17, still hasn't clicked out. 22 millibar. So let's say the last engineer came to this job and thought, oh, there's a screw there, I'll just screw that in. He's done that to it, made it 16. Well, unless the fan is capable of producing a 16 millibar draft or pressure, there's no way you're going to actuate that, is there? Do you see my point? So not all of them are like this. Some of these ones, the Honeywells are, but the majority, unless you know what you're doing, you could be looking for something because it clicks, it works. It doesn't mean anything. There could be a hole in it, as we found on this one, where it doesn't matter. You hear that click, still hasn't worked, still hasn't actuated. So as long as you get those values into your head, as long as you understand the mechanics of that, you'll be good to go. The two fans. Yes, we've all heard of test on here to check to see whether or not it's got continuity in the resistance value. So this one over here is 40 ohms. And that one's showing 40 thereabouts. They're pretty much in the same kind of ballpark. Fly lead in there. When I press the button, this will fire up. We're going to do this. Okay, so that's zeroed. This goes into there. That's it. Turn the... So we've got point... We pull it off the ground. 3.6, 3.5 millibar. 3.5 millibar. Explain why it's not drawing very much. If you put that base close to this desk here, then it won't be able to create too much suction, as you can see. Let's check the other side. So in theory, so you've got a bit of a discrepancy there, haven't you? Yeah? So in one direction it's drawing a lot, and in the other direction it's not producing much. 2. Okay, change this over. Plug this in. Okay, so you can see it's a lot lower there. Lift it up. 3 odd millibar. So that the first one we had was 3.5. So this one's a little bit lower. Check the other. And we got 2.2 on the other side. Let's do a little check. Pull this out. Now, I've blocked this one here. So, in theory, if we push this out, let's see what the difference is now. See if it's made any difference at all. So the first value we had. Now you got 4.5. So big difference there, yeah? Yeah? Check the second value. Yeah? So you kept the 2.2, but the other one has increased dramatically, yeah? So then you ask yourself, how come it's so different from one to the other? Well, this one in here has got a lot of scale debris in that. If you cleaned all of that up in an annual service, you would probably get closer to this figure, which was the 4-point-odd millibar. Yeah, so over almost 1 millibar or thereabouts, the difference. To show you guys the test that sometimes I will do to denote whether the fan is good, whether it needs servicing. You don't actually have to take any of this stuff out. You can do these tests with a digital manometer and the relevant mental astuteness. So you can do these tests, check these components without having to touch anything, and you can diagnose a lot of the problems, whether they're seal related, whether this is broken, whether it's blocked in there, whether the fan itself is all blocked on the other side, whether there's an issue somewhere else, a flue issue where it can't extract the air or bring in the fresh air, and get rid of the fumes. With a syringe, a T-piece, your ordinary bits and pieces. Clearly you're going to have one of these for doing things like the checks on Worcester Bosches, things like that, and you should kind of get to grips with this stuff. It's interesting to know where the issue is, and with a bit of time spent on the tools doing this sort of stuff, you can pinpoint issues, you know. It's great to be able to understand. Once you understand the mechanics of things that are positive, suction, normally closed, you'll nail it. Hope you enjoyed this video. Thanks very much for watching. See you on the next one. And with that, I've got to go.